Okay, today's topic is a review of the whole course. So homework 14 due, last homework, yay! And then remember to complete the actual course evaluations online. This is just for me in assessing and filling out end of semester reports. So the actual course evaluation will evaluate me as an instructor, not just your ability to learn the material. So fill those out for this class and for whatever other classes you are in. I have posted the lecture notes from this lecture. They're here. It's the course review. This is a good file maybe for you to save, download, keep for later, use it to study for the final, because it's a pretty good overview of thermodynamics the first semester in general. So there's just the highlights and the progression of material through the semester. So it would be a good study tool for you, and that's what we'll cover today. So again, final exam is scheduled Tuesday, May 2nd. So please be here, be early, make sure that we can start on time. Well, we'll start on time regardless of whether or not you're here, but I'll have to make sure the building's unlocked. That'll be the key. So way back at the beginning, we talked about the laws of thermodynamics. And originally we just talked about the first law and the second law. Then we introduced the 0th law and the 3rd law a little bit later. But the 0th law is the basis of temperature measurement. So if two bodies are in thermal equilibrium with a separate body, then they're also in thermal equilibrium with one another, even if they're not touching directly. First law is energy balance. Second law is the quality or directional properties of energy. And then the 3rd law is talking about the entropy generation or entropy creation as we move away from absolute zero. So at absolute zero, when molecular motion ceases, we can say that the entropy of a system approaches a constant minimum. And if we set that value as 0, then it would be 0. So entropy is relative because it's recognized in the change of state or in a process. So we can set a 0 value for entropy anywhere we like. Commonly in the tables, as it's tabulated, it's set at absolute 0. General forms of the energy balance equation. This should look fairly familiar. So Q net in minus work net out. Of course, we can write that in many different ways. We can rewrite that as Q in minus Q out and work in minus work out, but we'd flip the sign. So this is just in general form. For an open system, steady flow system, we now have m dot and then the enthalpy, kinetic, and potential energy terms. And if it's an open system unsteady flow, then we have work in, work out, heat in, heat out, and then these mass flow times enthalpy, kinetic energy, and potential energy is combined into this theta term, and that's equal to the change in the energy state of the system. So if it's an unsteady flow system, it means it's not at steady state, that there can be mass accumulation or energy accumulation or drain within the system. So the energy or the mass is changing over time. Whereas with a steady flow system, mass is not changing, energy level is not changing, but you have different things coming in and out. Problem solving techniques. This was an important one for you to hopefully learn and follow throughout the semester on homework, on exams, on quizzes. You can use this in other classes. These steps are very helpful if you get stuck. So restating the problem in your own words just helps make sure that you understand the problem and that you know what it's asking. Drawing a picture, a schematic with known property values helps you to really organize this problem, make sure that you, again, understand the problem, what the picture looks like, and then also pull out important key pieces and put the known property values on there. List any assumptions and approximations. You know, is anything constant during this problem? Is there any heat transfer? Do we need to worry about boundary work? Looking for those things. Is it steady flow or unsteady flow? Is it an ideal gas or not? That those are very important to identify either from the problem statement or the schematic to make sure, again, that you're not missing something. So in many cases, it's very easy to fix the first state in a lot of the problems that are given. And the second state, maybe you'll have one property value that's given explicitly. Well, by thinking about these assumptions or these approximations, you can say, okay, well, the temperature is constant during this problem. Oh, okay, I do know T2. I do have a second property value. or maybe the pressure's constant because it's a piston cylinder device with no external forces acting on it. So it's so important to be able to understand, identify, and draw that schematic. Look up any properties that aren't given, and then start applying your physical laws. And these may be somewhat iterative. You may start applying physical laws and then realize you actually need to go back and look up some more properties. Or you start applying the physical laws and you think, oh, okay, wait a minute, maybe there were some assumptions that I missed. So you need to make sure that your assumptions match your physical laws as well. And then at the end of the problem, look at it and think, is this answer reasonable? For example, if you come up with a negative pressure, okay, that's probably not a reasonable answer. That's not going to make sense. Or if you're trying to determine cost and it's saying it's $120,000 per month to operate your air conditioner at home, that's probably not a reasonable answer, right? So you can use that logic to determine that. Processes are the changes that a system undergoes between states, and the path is the set of microstates that it follows from one state to another. So this process path will be represented by a solid line if it's quasi-equilibrium, meaning we know for fairly certain that it's passing through all those states as we go along that process. And then a dashed line if it's a non-quasi-equilibrium process. So maybe it's not ultimately clear that it's following that path, but that's what we believe it's following. And then if it returns back to its initial state, it's deemed a cycle. Okay, so this should all be just review. Closed systems are ones where mass cannot cross the boundary of the system. However, the boundary may move. So volume can change or not. Energy can cross the boundaries. We can have work inputs. We can have heat inputs. But we don't have any mass flow across the boundary. So that's the main distinction between open and closed. It's closed to mass, not necessarily to energy. And we've seen a lot of examples of closed systems where it's a piston cylinder device and the boundary moves, which in many cases we have to remember to add in that work term as we undergo the process or undergo the analysis of the process. Open system is also called a control volume, and it's a system which includes mass flow. So there may be openings where mass is flowing in, mass is flowing out. There may be just an inlet, there may be just an outlet. An open system is any of those cases, but we can make the distinction in subcategories of open systems that are steady flow and unsteady flow. And again, we can have real boundaries or imaginary boundaries. So the opening of a nozzle would be an imaginary boundary. There's not actually a physical structure there, but it's what we're calling our boundary. And then the boundaries can be fixed or they can be moving, like in a piston cylinder device with some sort of a valve where things can enter and exit. So we talked about properties a lot during this class, and hopefully you understand the difference between intensive and extensive properties. So extensive properties are those that depend on the mass or the extent of the system. So mass and volume are certainly extensive properties, because if you were to draw an imaginary line in between or dividing your system in half, intensive properties wouldn't change at all. They're independent of the mass, whereas extensive properties would be divided in half. So mass and volume depend upon where you place your boundary, whereas temperature, pressure, and density or specific volume do not. And we can take an intensive or an extensive property like volume and turn it into an intensive property by dividing through by the mass. And anytime we divide something through by mass, we turn it from an uppercase letter to a lowercase letter. That's the nomenclature we use in this class. And the state postulate is that the state of a simple compressible system can be fixed by two independent intensive properties. Okay, so when we talked previously about fixing the state, that's so important that we use independent properties, and they have to be intensive properties. So temperature and pressure are independent in the compressed liquid region and the superheated region, but if we're operating under the dome, they're not independent. During a phase change process, temperature and pressure are very much dependent on one another. So they're not independent properties. They can't be used to fix the state under the dome. We need to have an additional property to fix the state, and we can use that to determine how far along that line we are. We might know that we're under the dome. We might know that the temperature and pressure are specific values, but in order to find where we are along that line, we need one additional property. The temperature scales that we've used in this class are primarily Celsius and Kelvin, but also Fahrenheit and Rankine. You need to know how to convert between those temperature scales. And if you are given information in a problem that's in Fahrenheit, you don't need to convert to Celsius and then to Kelvin. You can just convert directly to Rankine if you need to do that. So be aware of how to do those conversions and do them correctly. Last exam, or maybe the one before, there were some issues with that. So be careful about that. And then also note that the change in temperature in the Kelvin system is the same as the change in temperature in Celsius. So if you're calculating a delta T, you don't need to do any conversion to change it to a delta T, Kelvin, and Celsius. They're the same because the slope of the line is exactly the same for those two. There's just an offset. The same for Fahrenheit and Rankine scales. We talked about pressure and calculating pressure. So the absolute pressure is the actual pressure at any given point. Gauge pressure is the difference between your actual pressure and atmospheric pressure. So like, for example, when you're pumping up a tire and you measure the tire pressure, you're measuring the difference between atmospheric pressure and the pressure inside your tire. So that's what a tire gauge will measure. And then vacuum pressure is the same thing, but if you're sub-atmospheric pressure, we call it a vacuum pressure, and then say it's a positive value rather than a negative gauge pressure. So they're the same thing. Absolute pressure is just the absolute pressure, the actual pressure. So atmospheric pressure in this room is probably pretty similar to the atmospheric pressure outside. It's also considered the absolute pressure because there's no difference between this and atmospheric. However, if we start pumping lots of air into this room, we may have a higher pressure slightly in here than outside, or vice versa, because of a storm rolling in. So understanding the difference between those, also knowing how to calculate pressure with depth, that it will increase linearly with depth, and that relationship is linear with the density and the height. So we can add density times gravity times the height to the atmospheric pressure to determine the pressure at any depth. And if there's multiple fluid layers, we can just add them in series, that if we know the individual density of each of those fluids and the depth of each of those fluids, it's fairly easy to do that. Heat and work are both energy transfer mechanisms, and they're in kilojoules if we're working in the SI system, and in the English system it would be like BTUs. We recognize them in the process. There's no such thing as like this system has a certain amount of heat associated with it, or this system has a certain amount of work associated with it. We only see the effects of it as a system is undergoing a change or undergoing a process. So they're recognized at the boundary of the system, and as such, we can define our boundaries to either include work interactions or not. So it's very important to remember that as you're defining your system, as you're drawing your boundary, that you can purposely put your boundaries in such a way that you would need to know work interactions or not. An example of that is a heat exchanger, right, in steady flow engineering devices, that we can use the boundary of the heat exchanger as the boundary of our system. And by doing that, we don't have any heat interactions. We just have an inlet and an outlet with mass flow. However, if we wanted to know what heat interactions were going on inside the heat exchanger, we would use each individual fluid as its own system. Then we could take into account the heat that's crossing the boundaries there. So anything that happens within the boundaries of the system, we don't necessarily need to know, or it's not accounted for in our calculations. So if we're just trying to find mass flow rates, we can look at it without needing to know the heat transfer inside. Okay, that's not that out. When we talk about energy that's being transferred to a system by heat, if we add heat to a system, it increases the temperature. As we remove heat from the system, it decreases the temperature. We found out later in the semester that it also serves to increase the entropy of the system when we add heat and decrease the entropy of the system when we remove heat. And a process in which there's no heat transfer is called adiabatic. And it's important to distinguish between adiabatic and isothermal, because in some cases students might think, oh, well, if the system is adiabatic, it also means it's isothermal, which is not necessarily the case, and is many times not the case. So those two are not synonymous, that your temperature won't change if you don't add heat, because your temperature can change with mass flow, and it can change with work interaction. So it's not a given that it's isothermal if there's no heat transfer. We can transfer heat via conduction, which is actual physical contact from one surface to another. Convection, which is heat transfer between a solid surface and an adjacent fluid, and then radiation, which is transmission by electromagnetic waves. And these three topics, we don't even really get into this in this class. That's a topic for heat transfer itself. We spend a whole semester talking about that. We can transfer energy by work, and in order for something to be considered work, either there's a force acting on a boundary or the boundary is moving. So those two mechanisms are what we consider to be work. Everything else is heat transfer. And again, it's work is recognized at the boundary of the system. So if there are things going on inside the system, but we haven't drawn our boundary to include it, or it's not crossing the boundary at all, then we don't have to worry about those work interactions. And as with other nomenclature, if we put a dot over something, it's energy per time, or if it's a dot over the work, it's work per time. And then we can refer to those as kilowatts or kilojoules per second. So distinct different units. There are many types of work, and we've used electrical work in this class. I think we maybe did a problem with shaft work and spring work. So we also, there's work required to change the potential energy of something, which is recognized as we go through an elevation change or distance. And then work is required to accelerate a body, which is the same thing as kinetic energy. So we view those also as work terms, because either something is moving or a boundary is moving. So they qualify under work. We can also transfer energy by mass flow. So in an open system, when we have mass flow crossing the boundaries, we also have this energy associated with not only bringing mass into the system, so we're adding energy just because this mass has some energy associated with it, but there's also some work involved in pushing other pieces of fluid out of the way so that this mass can come into the system. So we take into account both of those things in the flow work and the internal energy change. So we can rewrite that equation, En minus E out equals E2 minus E1, and that's the single flow, single stream steady flow version of the energy equation. We've seen many different forms of the energy equation this semester, so knowing what form to use, what applies when, is also important. We've talked a lot about efficiency in this class, and we've looked at efficiency in a lot of different ways. The first way that we looked at it is if we're trying to determine something that indicates the performance of our system, that the basic way of looking at that is that we have some desired outcome or a desired output, and then we're required to put something in order for that to happen. So if we think of efficiency in those terms, that it's a desired output over a required input, then it's easy to apply it in many different situations without necessarily having to memorize the equations for those efficiencies. So if we're looking at steady flow devices, or if we're looking at turbines versus compressors versus something that's work consuming or work producing, that we can figure out that performance for a heat pump, for a heat engine, that it's we don't have to necessarily memorize all the terms involved. If we just remember this, okay, what am I putting into the system that's required, and what am I trying to get out? And then if we calculate efficiencies of each individual pieces, we can multiply those efficiencies together to find combined efficiencies. Pure substances are ones that have fixed chemical composition throughout. So we looked at pure substances as our working fluids in many of our open systems, and also in our closed systems that we had pure substances within. And we make that assumption just so that we can easily analyze property values, that even though air is composed of many different things, like even water vapor is in air, but it's nitrogen and lots of different things, that we can simplify it and just look it up as, you know, air, that air has a table in the ideal gas tables and water has a table in the ideal gas table. We don't need to necessarily know all the different components of how the hydrogen and the oxygen change with temperature. We just look at it itself. We've looked at phases, so we have solid, liquid, gas. I think you understand that fairly well. Main important point of that is that solid is a lower energy state, but it's a lower entropy state as well. It's more stable, more readily defined, whereas as we increase the motion of the molecules by adding heat, then we have higher energy, but we also have higher entropy. So those two ends of the spectrum. TV diagrams, we talk a lot about the dome in this class, so understanding what that means physically. We have a compressed liquid region to the left of the dome and a superheated region to the right of the dome, and everything under the dome is considered a saturated liquid vapor mixture. It's important to know how to calculate quality, to be able to identify what state you're in. So as you go to property tables and you look up you know, pressure and temperature, are you able to identify whether you're superheated or whether it's a saturated liquid vapor mixture? And if it is a saturated liquid vapor mixture, do you know how to find the quality? Okay, that's really important. So we can look at the dome again on the PV diagram as well. On the TV diagram, we had lines of constant pressure, but on the PV diagram, we have lines of constant temperature. But there's still that very distinct dome region, which we see even later on the TS diagram also. So hopefully this is all review and it's like super easy for you. But using the tables, we have properties with the sub F subscript means it's liquid properties, and the sub G is vapor properties, and then we can calculate the difference between those two, and we call it VFG, which is VG minus VF, or HFG, which is HG minus HF. But calculating quality is, I think, maybe the Achilles heel for some of the students in this class, that it's the mass of the vapor divided by the total mass of the mixture. So you're trying to figure out how far along that line you are. If it's a line of constant pressure, constant temperature that's proceeding horizontally through the dome, you want to know exactly where on that line you are, because pressure and temperature don't do it. They just tell you you're somewhere on that line. So if you know either the fraction of mass that's in a vapor or liquid state, or if you know another property value, then you can use that information to calculate the quality. And using the quality, you can calculate all of the other property values to tell you where you are in that fixed state. We use the ideal gas equation of state in a couple of different forms, and it shows up later as we perform analysis on steady flow devices and as we look at isentropic assumption and things like that. Again, you can only use the ideal gas equation as it is applied to ideal gases, right? It doesn't work for water, it doesn't work for refrigerant. You'll get answers that are very, very wrong from where they should be. And if your mass is fixed, so in a closed system dealing with an ideal gas, you can set M1 equal to M2, which means that P1V1 over T1 is equal to P2V2 over T2. Only works if your mass is fixed and it's that they're equivalent quantities at the same at each state. Some other equations of state that we did homework on, but we are not going to have these on the final, just so you know. This is just for future reference later if you need to use them. The reason that we can't use the ideal gas equation for non-ideal gases is because their behavior is distinctly different. That the ideal gas equation prescribes a certain set of parameters that help to identify how a gas will react under certain pressure conditions. So if you increase the pressure, what happens? If you decrease the temperature, what happens? And it's it's related to the gas constant of the system, or it's linearly changing with the gas constant of the system. So we can see that some gases behave like ideal gases at very, very low pressures, at very, very high temperatures. But anytime we're operating anywhere close to the dome, or in particular at the critical point or near the critical point, that our ideal gas behavior sort of goes out the window. We did learn how to calculate and use a correction factor Z that allows us to account for non-ideal gas behavior, and just using these same equations, putting in this correction factor gives us a fairly good approximation, or guess, as not guess, pretty good approximation for ideal gas behavior. This is derived using the principle of corresponding states. So there's this idea that if we divide the actual pressure of our non-ideal gas by the critical point, and we do the same thing with temperature, we divide by the critical point temperature, that we can have these reduced pressure, reduced temperature, and then also a reduced specific volume if we want to calculate it that way. That when we do that, we normalize our working fluid by its own critical point. We find that they follow a very similar trend. Okay, so these trends have been plotted on a compressibility chart. So if we calculate a reduced pressure and calculate a reduced temperature, we can look up a compressibility factor that allows us to make a pretty good correction to our ideal gas equation to get us closer to the correct values that we would find if we were to look it up in a table. So we did a little bit of that this semester. It's a good concept to remember from that. We also talked about polytropic expansion or compression, and that in some cases we have this behavior that can be modeled quite readily by this relationship, PV to the N is equal to some constant. So for an ideal gas, then the constant is the gas constant, but it's PV equals RT, N is equal to 1, and C is equal to RT. So if we have knowledge that our gas follows some polytropic expansion or compression, then we can use these particular equations simplified in order to apply them to our system and calculate whatever unknown property values we're looking for, or to calculate the boundary work depending on what we're looking at. Again, this is a very specific case where it only works if our gas is undergoing a polytropic process. Okay, so you can't use this for water, for example, in a cylinder. That won't work. It has to have that relationship, and that functional relationship between PV has to be known in order to apply these equations. We've talked about boundary work. Boundary work is just the integral of P dV, and if it's a constant pressure process, then that P comes outside the integral, and we just integrate dV, which gives us V2 minus V1. So we simply need to know the distance that cylinder moves, or the change in volume, in order to calculate how much boundary work is being done. We can also figure out how much boundary work is being done by numerically or graphically calculating the area under the process path. So in the case where that's a linear path, we did many examples where we just simply plot it graphically and use geometry to figure out the area under the curve. Otherwise, we need to know the relationship between pressure and volume and then calculate the integral. So sometimes we have that, and that relationship is fairly easy to integrate. Sometimes we have it and it's a beast to integrate, and then other times we just have data points and we'll have to maybe graphically figure out the area under the curve. For a closed system, we have our energy equation is equal to the change in internal energy. But we found in many cases that if it's a closed system with boundary work, that we can take that boundary work term and move it onto the other side of the equation, and we come up with this other term that's delta U plus P delta V, okay, or the boundary work. And this has been lumped together into a term called enthalpy. So enthalpy accounts for the internal energy plus the boundary work in a closed system. And in an open system, it accounts for internal energy plus the flow work. So some example of that would be phase change along a saturation line, that's a constant pressure process. Also in a piston cylinder device that's frictionless, it's a constant pressure process. So part of your system analysis is identifying any property values that might be constant and pulling that out right away, writing that down, isobaric, isothermal, whatever it might be, that if it ends up being a constant pressure process, it makes the boundary work very easy to calculate. However, you can't do this if it's not constant pressure. You can't move it to the other side of the equation because P is changing. The specific heat is the amount of energy required to raise a unit mass by 1 degree. And we can either do that at a constant volume or a constant pressure. So we have two different specific heats that are defined in two separate ways. C sub V is related to the change in internal energy. So if the volume is maintained constant, then we don't have this, this boundary work going on either. So we have CV dt is equal to du. And for specific heat at constant pressure, then maybe we do have flow work or boundary work, but it's the constant pressure process. So we have C sub P dt is equal to dH. And we use C sub P quite often if we can make that assumption that it's not changing significantly or it's a small change. So we can determine delta U and delta H three different ways. One, we can use tabulated data for both, which is pretty easy, assuming we have tables that are accurate and up to date. We can use the functional relationship between pressure and temperature and integrate, which is kind of cumbersome and not really fun to do by hand. Or we can say, okay, I know C sub P and C sub V maybe are changing, but I'm going to assume that it's just some average value. And it's pretty accurate to do that if it's a small temperature change or small temperature interval. And you can calculate C sub P average two ways. You can either find it at the average temperature, if you know your initial and final temperature, or you can look at each, the beginning and the end, and average those two values. And we did do some examples towards the end of the semester where we didn't know a final temperature, but we needed to use C sub P or C sub V. So we guessed a final temperature, and we calculated using that. And then we came back and calculated our final temperature and just tried to see how close it is. So if it's really far away, then we say, okay, I'm going to redo this calculation with a new estimate using a new C sub P, and you iterate until you actually find a value that's close. I've already said to you I'm not going to give you a problem like that on the final where you have to iterate. But it's important to know how that process works, and that many times in design you don't know the final outcome until you build something, right? So you have to guess, okay, maybe my knowledge of previous systems, I know that they get about this hot. You know, so then you say, okay, I'm gonna guess this final temperature. Then I'm going to actually calculate what the final temperature should be, and then redo your calculations that way. So a lot of engineering starts with an educated guess, and this is no different. Steady state devices. We in chapter 5 is full of steady state devices, and it's probably one of the more difficult chapters, I think, to get through and understand. But then once you do, you can apply these principles across the board to any steady state device, any kind of problem that it might throw at you. So some consequences of steady state: usually the volume's not changing, so we don't have any boundary work. Usually the mass is constant. Well, always the mass is constant for steady state. So dm dt is 0, and then the energy state's not changing either, so dE dt is 0. So we have our mass flow in is equal to our mass flow out, and our energy in is equal to our energy out. So again, looking at those forms of the energy equation for steady state devices, where we have in on one side of the equation, out on the other side of the equation, we can switch those terms back and forth, making sure we flip the signs as we do. But these are the basic equations that we use. So we need to look at each of the individual terms for these steady state devices. That Q dot, or Q, is the heat transfer between the control volume and the surroundings. And it will be a negative value, or it will be an out value if the control volume is losing heat. If it's adiabatic, then there is no change in heat, or heat gained or lost. Work dot is the power. W dot And if there's no boundary work, we just need to look at electrical work or shaft work. And if we know those values per unit time, then we'll have the power output. If we multiply by a time interval, then we'll have the total work done. Then if there's none of those, we'll assume that our work dot is 0. The enthalpy change of the fluid accounts for the internal energy changes plus the flow work, which is, again, there's energy coming into the system just due to the energy state of this fluid, but then there's also energy involved in pushing other pieces of fluid out of the way. So it's almost like boundary work. It's analogous to boundary work within your system. And many times we can approximate it using the C sub P approximation. Change in kinetic energy. Usually we neglect this term, but if it's in your equation, be very careful and watch your units. Good rule of thumb is if the problem gives you velocity, use velocity, right? But 1,000 meters squared per second squared is equal to 1 kilojoule per kilogram. So if you don't make that conversion, then your calculations will be way off. The same thing goes for the change in potential energy. Be very careful about your units on that. And in many cases, that one is neglected because it's pretty insignificant. But again, maybe it will be in there. In general terms, when we perform the mass balance, it's mass in minus mass out is equal to the change in the mass of the control volume. If it's a steady flow system, then the control volume mass is not changing, so it's just the sum of the mass flow in is equal to the sum of the mass flow out. And if it's single stream, we just have an m dot in and an m dot out. And then if it's a steady flow incompressible stream, then our volume flow rates are equivalent. And if it's steady flow incompressible single stream, then we can just say that the velocity times the cross-sectional area is equal on the inlet and the outlet. So knowing again which assumptions you can or cannot make and how it simplifies your equations is pretty important. Because in the final you'll have just this equation sheet, it's actually 2 pages now, with just tons of equations. It's up to you to know how to apply them and use them, because it's very easy to use the wrong equation just because you see, oh, there's temperature, there's pressure, that's what I need, right? You need to know what assumptions can be made. Okay, so nozzles increase the velocity of a fluid, diffusers decrease the velocity of a fluid. There's no work interactions unless there's, maybe sometimes there's like a heater inside the nozzle, like a little electric circuit or something. Usually it happens so rapidly there's no heat transfer, don't have to worry about potential energy. However, a change in kinetic energy is pretty important because that fluid can change, the velocity can change fairly significantly. In some cases, coming into the nozzle, it's almost 0, and then coming out of the nozzle, it's pretty high. With a turbine or a compressor, we have mass flow in and out, and then if it's a turbine, there's a network output, and if it's a compressor, there's a work input. So kinetic energy is usually 0, but sometimes we need to know it. If there's velocities given and you're asked to calculate it, I would calculate it, being careful about units again. And our work interactions are never 0. You don't know necessarily about the heat transfer unless it's given in the problem. That usually there's not a significant heat transfer because they're well insulated, but that's not always the case. And as we saw with compressors, there is an advantage to actually removing heat as we compress these fluids, that's a positive thing. So later in the semester when we started looking at the isentropic compressors and even doing better than that by trying to operate an isothermal compressor, that there is significant heat transfer involved there. Throttling valves are a constant enthalpy process. And it's any kind of flow restricting device. So it could be a valve, it could be a plug, it could be just a very narrow tube that doesn't allow flow to pass through readily, causes significant pressure drops without needing to perform any work, which is kind of nice. And for an ideal gas, enthalpy is a function of temperature only. So for a throttling valve using an ideal gas, the enthalpy will be constant and the temperature will also be constant, so they're also isothermal. Mixing chambers are any devices where one or more or two or more fluid streams come together. and so they can mix together and then go out two separate ways, out one separate way. A lot of times it's just an elbow with cold water coming in, hot water coming in, and then warm water coming out. There's usually not any work interactions unless there's some sort of a stirring device in there. Heat transfer to the surroundings is usually zero, and kinetic and potential energies are usually zero. So you're just interested in this, these relative mass flow rates of each of the streams and their enthalpy values associated with them. So you're changing the energy of the system just by mixing fluid streams of different temperatures, different energy states, and in some cases different flow rates. Heat exchangers exchange heat between fluids without them actually physically coming in contact. Usually there's no work interactions, and the kinetic and potential energies are negligible. And we talked about defining the system. So if we define our system as the boundaries of the heat exchanger itself, then we won't have any heat interactions with the outside. However, if we look at the individual fluids themselves, then there most certainly is heat transfer associated with that heat exchanger. That's the purpose of it, is to transfer heat from one fluid to another. And the direction of the heat transfer will always be from the hotter fluid to the colder fluid. In pipes, they're somewhat boring if there's work interactions or not, heat interactions or not. So we just have to look at the pipe individually and see what's going on with it, whether or not there's velocities that are significant or significant elevation changes. We don't necessarily make any grand assumptions about pipes. It just all depends on the problem when you get to it, and being very careful to look at it and see, okay, is heat being lost? Are there any energy, work interactions? What's going on with this particular pipe before you can say anything about it? So during steady flow processes, the properties of the control volume itself are not changing with time, although there may be different properties at the inlet and the outlet. But the control volume itself is steady, that the properties are not necessarily uniform across the control volume, but they're steady with time, they're not changing. During unsteady flow, the properties of the control volume do change with time. And so we have to look at it over a finite time period, saying, okay, we're analyzing this system from this point to this point, and we want to know what changes have happened, how much mass was accumulated, or how much mass left the system. And the control volume is not necessarily fixed in size. It could be a piston cylinder device. We could cause the boundaries to move if needed. So the analysis is slightly different from the steady flow because we have that additional term on the right-hand side of the equation, or additional terms. But again, if we just go back to our energy equation, start from the beginning, and are very careful when we start canceling out terms that we have in and we have out is equal to the change in energy state of the system. So that change in energy state is equal to the internal energy, kinetic energy, and potential energy of the system as a whole. So if the system itself is moving or changing in elevation, if it's accelerating, whereas that theta term on the left-hand side of the equation deals with the fluid flow of the streams coming in and out themselves, so whether or not they have a kinetic energy associated with them that we need to account for. So if those terms are negligible, then we just simply have the Q in minus Q out plus work in minus work out, or we can flip the sign and do it that way, is equal to the mass flow out minus the mass flow in times the respective enthalpies of those fluid flows plus M2 U2 minus M1 U1, okay? And that mass flow can be on either side of the equation. Again, we just have to be careful about signs. Okay, heat engines. So heat engines receive heat from a high temperature source and convert part of that heat to work, and then they have to reject heat to a lower temperature sink. And usually we have a working fluid that is changing phase in the process, so it's going from a liquid to a vapor. We don't often need to know necessarily those energy interactions if we're looking at the large-scale macro version of the heat engine itself. However, because we have this knowledge of steady flow engineering devices that we already learned in Chapter 5, we can look at the individual components of a heat engine to determine some of these larger scale property values. So it operates on a cycle of steady flow engineering devices such as a boiler, turbine, condenser, and a pump. So we can, again, look at those pieces individually to determine Q in, Q out, work in, or work out. Or we can maybe we're given those values. We know that it's losing a certain amount of heat, or that it's gaining a certain amount of heat, and that we have some maybe desired work output. So we have to determine how much heat needs to be added to the system. So a lot of different ways to construct these problems. We calculated thermal efficiency, again, as a desired output over a required input. And for a heat engine, our desired output is a net work out, and the required input is just that Q in, or Q sub H, from the high temperature reservoir. And again, as we talked about the Carnot law, we'll talk about it in a minute, or Carnot statements, the thermal efficiency of a heat engine can never be 100%. It's usually less than 60%. So that Q that's coming into the system can never be converted to work totally. Okay, only a fraction of it is converted to work, and then the rest of it is rejected to a low temperature reservoir. KelvinPlanck's statement is that it's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. And then Clausius' statement is similar, that it's impossible to construct a device that operates and produces no net effect other than transfer of heat from a low temperature body to a higher temperature body. And we talked about how these two statements are manifestations of the second law of thermodynamics. So the first one, that energy has a direction to it. Actually, they both kind of talk about energy having direction. First one is more about the quality of energy. The second one is more about the directional properties of energy. That those are important to remember and know. With refrigerators, we have heat being removed from a cold space and then deposited to a hotter space, warmer space. And that's being done by virtue of a refrigerant that's flowing through this thermodynamic cycle consisting of condenser, compressor, evaporator, and an expansion valve. And again, our performance or our effectiveness is the desired output over the required input. So in a refrigerator, your desired outcome is that you are making a cold space colder. And then in order to do that, you have to put some work into the system. So again, just remembering that idea of, okay, what is the goal of this device to make something colder? Okay, so what's required? I need to put work into it. That's the best way to remember efficiencies and coefficient of performance, that if you keep that in mind, that you should be able to figure out what to do. Heat pump is pretty much the same cycle as a refrigerator, but instead of removing heat from a cold space, that's not your desired output. Your desired output is to add heat to a warmer space. So it's Q sub H over the work net in. And again, as we analyze these systems, we may be given these macro values of like, okay, you have work net of this amount and a Q sub H of this amount, calculate the coefficient of performance. Okay, that would be a pretty easy problem, right? Or maybe they'll say, okay, you're losing heat from your house at this rate, and the condenser in your heat pump has this inlet value and this outlet value. Okay, so then you use that information to calculate Q sub L, and then you use the other information to calculate Q sub H, and then using that, you could calculate the work in. Using that, you could calculate the coefficient of performance. Okay, so being able to apply this energy equation to specific systems or steady flow devices is important. So as you read your problem statement, you may have to define your system boundary as one individual device, as the whole thing, or maybe you need to do two separate problems because you have so many unknowns, and analyze an individual device and then analyze the whole thing. As you do that, be very careful about these heat and work interactions, because if you're just looking at the condenser, you don't need to know Q sub H. That's irrelevant information. If you're just looking at the compressor, you don't need to know QL or QH. You just need to know the work interaction and being able to calculate that. So as you draw your system boundaries, make sure that you understand why you're using that as your system boundary. You know, what unknown are you solving for? And then also, if that's your system, you don't care what's going on in the rest of this process. You're only looking at that itself. And then, you know, of course, be careful about assigning those values. So if it's talking about heat being lost from a house at a certain amount, that's not how much heat is coming in at Q sub L. That's what Q sub H is replacing. So there were some issues with that on the third exam. Had some struggles with that. So go back and look at that if you were one of those people who had that issue. We talk about reversible versus irreversible. So reversible process is one that we can return back to its original state, and sometimes we can do that internally, meaning that the device itself, maybe we can return to its original state, or sometimes the surroundings can be returned to their original state. And then totally reversible devices are when the system and the surroundings return, both of them, to their original state. This is usually found in practice, in theory, but not in practice, that we can approach totally reversible, but that in actuality there's always irreversibilities within our systems, either due to friction or head loss or heat loss or chemical changes, things like that. So some irreversibilities that we often find: friction, unrestrained expansion. So if it's a rapid change in pressure, it can cause to rapid change in temperature, which means that heat is being lost from the system, or depending on which side of it you're looking at, heat is being gained somewhere else. Electrical resistance, we have electrical work that's being converted to heat, and once it's changed to heat, that's an irreversible process, because we can't then take that heat, put it back into the wire, and convert it back to electricity. That only a fraction of it, maybe if we have the right types of materials, can be converted back to electricity. So heat transfer is always a one-way process. And then anytime we mix two fluids together that we can't separate back out again, chemical reactions are irreversible. And then if you know, an inelastic deformation, so like a car accident, you know, your car's never going to be the same. That you can return it back to the original shape, maybe with new parts, but even if you knock out all the dents or whatever, it's never going to be quite the same again, right? Okay, we talked about perpetual motion machines, and that real processes have to satisfy both the first and second law. That we may have some device that purports to do something really spectacular, and a YouTube video proves it, right, that it can do this thing. Well, if it's violating first law or second law, then it's not really doing what it claims to do. You can show a lot of things on a video that are not true. So if it violates the first law, that means it's violating the energy balance or conservation of energy. Then it's a PMM1. If it violates the second law, then it's a PMM2, meaning that either it's converting 100% or significant too much heat to work, you know, like its thermal efficiency is greater than the max possible, or you know, energy is being transferred in the wrong direction or something like that. Then it would violate the second law. So we understanding the distinction between those two, and there were some good examples on that exam. So the Carnot cycle is a reversible cycle that we use as a model for like best case scenario, and it's this ideal that we kind of can compare our real cycles to. And it consists of 4 steps, very important. I would suggest that you figure out how to both draw the Carnot cycle and repeat those steps if needed. So we have reversible isothermal expansion. In order to have isothermal expansion, we have to add some heat from an energy source. And then we have adiabatic expansion, where we continue to expand the gas, but now we're not adding any heat, so the temperature decreases. Then we reject some heat to a heat sink at T sub L. So as we compress this gas, it will necessarily heat up, but we remove heat in order for the temperature to remain constant. And then we continue to compress further, and the temperature increases back up to T sub H. So those 4 steps are the reversible Carnot cycle. And if we operate them in the reverse direction, then we have the reversible Carnot cycle. The 2 Carnot principles were, number 1, that the efficiency of an irreversible heat engine will always be less than that of a reversible one. And then the second is that all reversible heat engines operating between the same 2 temperatures will have the same efficiency. So those 2 Carnot principles are good to know. The Carnot heat engine operates on the reversible Carnot cycle, meaning the standard Carnot cycle that is a reversible cycle. And then we can use the knowledge of our temperature limits in order to calculate the reversible efficiency of that device. So for regular heat engines, we use the desired outcome over the required input, which would be work out over QH or QN, which we can rewrite and rearrange because work out equals QH minus QL. If we play with that, then we can write it as 1 minus QL over QH. But for the Carnot cycle only, we can replace QL and QH with the temperatures of the reservoir, and that gives us the highest possible efficiency for any heat engine between those two reservoirs. And it's important to note that we have to use the absolute temperature scale on that we can't use Celsius and we can't use Fahrenheit. That has to be temperature in terms of Kelvin or Rankine. Carnot refrigerator operates on the reversed reversible Carnot cycle, with the outcome being removing heat from a refrigerated space. So we can similarly write a reversible thermal efficiency using the temperature limits as our inputs as we take our previous equation and rearrange it. So that's the reverse coefficient of performance for a refrigerator, reversible coefficient of performance. Same thing can be done for a heat pump, where we're now using the reversed Carnot cycle, but we're just changing where our QH and our QL are going. So rather than removing heat from a cold space, we're actually adding heat to a warmer space. And again, we can calculate that Carnot efficiency for a heat pump operating on the Carnot cycle. Okay, entropy. So this is probably the least favorite subject of most of the students because it's a little bit more difficult to understand. We talked about that for a reversible process, the change in entropy is going to be that integral of del Q over T. So if we looked at a TS diagram, the plot underneath is the reversible heat transfer. But for an irreversible process, we generate some entropy during that process. So if we end up calculating the change in entropy for a process, that means looking at the system and the surroundings, and it ends up being negative, this entropy generation is negative, then it's an impossible process. That's not a process that could occur in real life. So this gives us another numerical value or a way to look at devices or processes and determine if they're violating the second law. So this, before we could just look at something and think, I don't think that's right, or maybe we look at it and we're not sure, it seems too good to be true. So if we apply the principle of entropy to it and calculate the entropy generation, if it's 0 or negative, it's probably not a real process. We can also look at the entropy generation for an isolated system, which would be a system plus the surroundings, and that value is always greater than or equal to 0. So it'll be greater than 0 for any real process and equal to 0 for a reversible process. The increase of entropy principle is just that entropy is always increasing, that there's always some entropy generated during a process, and it's not a property of the system. So just like heat and work are only recognized as we undergo a process, the same thing goes for entropy, that this entropy generation is recognized as we undergo some process, which means that we could get from state 1 to state 2 in a myriad of ways, and some of them may be more reversible than others. So we might create more entropy doing something a certain way than we would doing it another way or using a different process. So the same goes for how much work is required to do something, that it's dependent upon the process itself. And that value is always going to be a positive, or in the rare case of a reversible system, it will be 0. So the entropy of the universe is always increasing. We can look at individual components of the universe that have a decrease in entropy, but it's because it's increasing elsewhere by a greater amount. So let that keep you up at night. Entropy is a property value, so it's also something that we can look up in the tables. And the tables that we use in the book, I believe, are set at absolute 0. So the 0 entropy value is set at absolute 0 when there's no molecular motion. So we use it just like any other property value if we're calculating the entropy at a state. that we just look it up in the table. If it's a saturated mixture, we need to know the quality, and we can determine the quality sometimes if needed. For the compressed liquid tables, we can make the incompressible approximation where we just look up the fluid properties of a saturated liquid at the same temperature. And then for superheated vapor, we just need to know 2 independent properties to look it up. An isentropic process is one where the entropy is not changing. So we often can approximate engineering devices as adiabatic, meaning there's no heat transfer, and reversible. So if something is adiabatic, there's no heat transfer occurring. There's no reversible. I mean, it's reversible, meaning there's no friction or head loss or other things happening. Then we can say, okay, we're going to approximate this as a constant entropy process, meaning we're not generating any entropy by undergoing this process. Okay, so it allows us for the best case scenario analysis, which means that we are looking at the greatest work output, the least work input, because we're not throwing irreversibilities into the mix that serve to decrease our efficiency. And reversible adiabatic always means isentropic, but something can be isentropic if it's not reversible and adiabatic. It could be irreversible, but the heat transfer that is applied to the system makes up for any negative or any change in entropy. The Mollier diagram is an HS diagram, and it gives us at a glance the change in enthalpy and the change in entropy. So if we think of enthalpy change as like work and entropy change as like irreversibilities, this Mollier diagram gives us a good idea of how our system compares maybe to another system when it comes to how much work can be produced with the least amount of irreversibility in the system. So it's one that's used often to compare processes one to another, that ideally you would want that delta H term to be maximized and delta S to be minimized in order to have a more efficient or effective system. So we had a couple of equations called the Gibbs equations, which were derived using the relationship between enthalpy and internal energy, pressure, specific volume. So this is from the flow energy equation. So we can also look at it in terms of the other property values. So if we look at it in terms of internal energy or in terms of enthalpy, that we can derive these equations, which are applicable in calculating the properties or the changes in entropy based on other property values. So if we know a change in internal energy or the change in specific volume, then we can calculate the change in entropy. Similarly, if we know that something's constant, like let's say, for example, the volume is not changing, then the ds is just equal to du over t. We can cancel out terms in that way. For an ideal gas, we have additional relationships that if we integrate this functional relationship, that we can find our the entropy change for an ideal gas, assuming that the specific heats are approximately constant, is equal to that equation up there, CV average natural log of T2 over T1 plus R natural log of V2 over V1. And then the same thing for an equivalent expression using specific heat of constant pressure, so C sub P. These two equations, again, are only applicable when we are dealing with the entropy change of an ideal gas with constant specific heat. So we can't use it for water, we can't use it for cases where the specific heat changes significantly. But we can derive some additional equations in that same scenario if it's isentropic. So if that delta S is equal to 0, we can set the two sides of the equation equal to one another and come up with these relationships. And then using the specific heat ratio, which is K, then we can derive these equations as well. So these have three approximations that must be satisfied. One is that it's an ideal gas. Two is that it's constant specific heat. And then three is that it's isentropic. So this was that quiz problem that some got right, some got wrong. If we don't assume that specific heat is constant, we assume that it has some functional relationship between the specific heat and the temperature, we can use an additional tool called this S superscript 0, which is like a reference entropy, which is a function of temperature only. So it's equal to the integral of that C sub p dt over t. And we can use it in our equations to eliminate the functional characteristics or the functional reliance of C sub p on temperature. So by going to the tables to look up that piece or that component, then we can still use these equations just in a algebraic fashion without actually having to calculate an integral every time we want to know the change in entropy, because the integrals themselves have already been tabulated. So this is the exact analysis that if we set those equations equal to 0, we say that there is no entropy change. Then we can use this, this reference entropy to calculate, like we can use it to find a change in pressure. We can determine the second state of an isentropic process using that. If we don't know necessarily the temperature at the second state, we know the initial and final pressure, then maybe we can calculate this second reference entropy and then use that in the table to go back and look up the temperature. We can do a similar thing using the pressure ratios, where we have this relationship for constant entropy that P2 over P1 is equal to these reference pressures. So it's a similar idea to using that S superscript. And we can also do the same thing with volume. So there's three different ways using the pressure relations or the volume relations to help us find the final temperature for an ideal gas. And again, this is only for ideal gas isentropic process. Yes?
Quick question about that.
Yes.
EXP, is that like E to the...
Yeah. Yeah. It's just harder to type that, write that. Yes. Okay. For reversible steady flow work, that if it's undergoing an internally reversible process, then we can determine by manipulation of the energy equation and application of the Gibbs equation that the reversible work is equal to the negative integral of VdP minus the change in kinetic and the change in potential energies. And if we're ignoring those terms, then we can find that the reversible work is equal to that negative integral of VdP. So the work out is a negative VdP because the sign will be accounted for in the change of pressure if it's a negative. We talked about minimizing the compressor work by removing heat as we are compressing. So in the isentropic case, that's just a constant entropy process. We don't apply any cooling, then we use those equations. If we apply some cooling, meaning polytropic process where our N value is less than K, then we have a slightly less work into our compressor. And if it's an isothermal process, that's the best case scenario to minimize compressor work, that we have that equation there. And we did homework on that. That should be straightforward. We can also do multi-stage compression where we have a stage in between, and we can minimize the compressor work when the pressure ratio is equal to one another in those two equations. So Px over P1 is equal to P2 over Px. And we can calculate an isentropic efficiency of a compressor using the actual compressor work and the isentropic compressor work. So we're saying how closely does this resemble an isentropic process? If that efficiency is 100%, then our actual process is the same as our isentropic process. And the further away it gets from the isentropic process, the lower the efficiency will be. And this should all be fresh in your mind because you just barely did this on the homework. And then the same thing goes for the turbine, that we're looking at actual case and isentropic case. We can do the same for pumps, but in this case recognizing that the work of a pump is equal to V times P2 minus P1 because we're making the incompressible approximation. And then for nozzles, we look at the kinetic energies in order to determine those efficiencies. So we could perform a total entropy balance, Sn minus S out plus S gen is equal to the change in the entropy of the system, where that's the S final minus the S initial. And we looked at it for closed systems. So if it's an adiabatic closed system, then our entropy generation is just equal to S2 minus S1. And then if we look at a system plus the surroundings, then our entropy generation is equal to the change in entropy of both of those. For an open system, we have some entropy that's coming into our system with mass flow. So those equations apply. Hopefully, again, these are familiar to you. It's important to note that there is entropy change in the system due to heat transfer and due to mass flow. You have to account for both of those terms. And if there's heat transfer coming in at a certain location, we need to know the temperature of that location. Then we talked about the the vapor power cycle, which we looked at in both the isentropic and the non-isentropic, or the actual vapor power cycle case. So this one, very important for you to know how to draw that picture and those steps that are involved. So this is all recent stuff. I will spend less time on it because we're out of time. And you can perform the energy analysis using those steps. So we looked at deviation from ideal and how we can increase it. It would be good for you to know the ways that you could increase efficiency of a Rankine cycle. That might be a good exam question. And then in the last lecture, we talked about the air standard cycle and the assumptions that go along with that. So for this section, terminology is very important. There may be a diagram you'll be asked to label with all these terms and conditions on it. You might need to define any of these terms or conditions. And then it would be a good idea for you to know how to draw, like, for example, the Otto cycle or the diesel cycle and the 4 steps that are involved there. And then the Brayton cycle, which was for a gas turbine engine power plant. So final, you'll have 2 sheets of paper, just like the other exams. And I'll give you the equation sheets and property tables that you might need for the problems. Again, good hint, if there's a property table, you probably need to use it. So don't freak out and try to use the ideal gas law because you can't figure out how to find the water temperature or whatever. And it's comprehensive. Just by nature of this course, everything is comprehensive from the beginning to the end. You should have seen that pretty clearly today. But the emphasis is going to be on the stuff you haven't already been tested on. So entropy is a big part of that. Being able to calculate like actual and isentropic states, using with the Rankine cycle. And then there's going to be short answer problems, homework style problems, that it's going to be a mix, and it'll be slightly longer than any of the midterm exams. So it'll probably have more short answer questions and maybe the same number of homework style problems, but it's going to be a little bit longer. So you have 2 hours instead of an hour and a half. So good luck, study hard, and I'll see you on Tuesday morning, bright and early. Send me a picture of it. Ooh.